Welcome to week number 5 of the transportation seminar. Today we have two great speakers, David Hurwitz from Oregon State, an associate professor there, and our own Chris Monsere, associate professor at the Department of Civil Engineering. And be ready for some right turn bicycle action today. And they would prefer questions at the end. So thank you.
All right. Thanks, Miguel. So we're going to do a co-presentation today. So we're going to do a couple switches. This is a project that Professor Hurwitz and I did together using the Oregon State driving simulator and then some video analysis that we did at PSU. This is building on a couple of different projects that we've had some successful collaboration. And towards the future, we've got a few more. So let's get right into it. Normally, I'd give you an outline of what I'm going to talk about, but we don't have time for the outline because we've got so much material to present. So we first started the project by looking at sort of the crash history. So we looked at all of the 4,000 reported bicycle crashes in the state from 2007 to 11. And then we looked at the paths of the vehicles involved in that crash. So we looked at when the vehicle was turning right and the bicycle was going through. We looked at all those combinations where it would be a potential right hook collision. So we did it just from the data. We plotted it all out. There's a lot of other information about the crash that we looked at, but mainly we wanted to look at what the context where these right hook crashes are happening. So the right hook crashes are about 12% of the total crashes, bicycle car crashes. So it's a fairly large percentage of that type of crash. But in terms of severity, it's not the most severe bicycle crash. So in fact, this is on the Cabco scale. So K is fatality, A is severe injury. There are some of those, but they're relatively few. Some people have called the right hook crash the rear end crash of the bicycle world. So, but there are a lot of them. And when they do happen, and they tend to if they involve large vehicles, then that's where the fatalities sometimes arise between the right hook collisions. So if you saw from those pictures, we knew where the crashes happened. So we looked at the construct of where that was at. And not surprisingly, most of those, 74% of those, happened at intersections. We went a little bit further and we looked at the traffic control at that location. Most of those right hook crashes, 74% of them happened at signalized intersections. And then we went a little bit further from the aerial photography and looked at the geometry at those locations. And what you can see that 60% of those crashes happened at signalized intersections where there was no right turn lane but a bicycle lane. The other configuration, the next one that had the most, was no right turn lane and no bike lane. So 60% of the crashes happen in that configuration. So there's a bike lane, but there's no right turn lane for motor vehicles. So this is kind of sort of what you would expect when you think about that right hook crashes. Cars are turning, they're at signalized intersections. There's a lot of them, but the bike lane is to the right of the vehicle. So the right hook crash can happen at a couple of different time periods. It can happen right at the start of green. At a signalized intersection, the same thing can happen at a stop sign. But it could also happen in these two situations where the cyclist is either overtaking the motorist or the motorist passes the cyclist and then turns in front of the cyclist. So these are the focus areas of the research. We narrowed it down. We looked at the geometry. So we were going to study these. We were going to not look at this risk factor. We were going to look at these two risk factors at signalized intersections without right turn lanes and with bicycle lanes. So you'll see some of the pictures later on that we used in the simulator. So our method was a two-phase experimental setup. I thought it was a good idea that we decided to do it this way. We did a simulator experiment in the first phase where we narrowed down some of the risk factors and we identified those critical risk factors. And then we took those critical risk factors and then overlaid them with some traffic control and geometry solutions and did another set of experiments in the simulator. That allowed us to look at the most risky situation and then look at what the effect of the different design options would be. And the part we did in between was a field validation using some video to look at how well situations in the field mapped to the driving simulator. So with that, I'm going to turn it over to Dave, and he's going to tell you about the experiment 1.
Thanks very much, Chris. So let's dig in a little bit to the experimental equipment that we used for this particular study. There were 2 primary devices that we focused on. Let's start with the driving simulator. So at OSU, our driving simulator is, we describe it as a high-fidelity platform. That's this image right here. It's a 2009 Ford Fusion. It sits on a partial motion base, and it's surrounded by very large screens that present a visual world that we can code into any configuration that we're interested in. On tangent segments of roadway, we can replicate acceleration and deceleration with high fidelity. When you're sitting in the driver's seat, all of your inputs into the vehicle, turning on the steering wheel, depressions on the gas or the brake, all of those are registered in the system, and we can record information at high rates, 60 hertz, for all those different performance measures. This is an image taken from the driver's seat as a vehicle is interacting in the presence of a bicycle. The second piece of equipment that we used in this particular experiment was our mobile eye tracking device. It's demonstrated here on one of our very able graduate students. So it's a head-mounted system. You basically wear a set of sports goggles. There are 2 cameras, one that's tracking the pupil of your eye, another that's filming the visual world as you look around it, and we have infrared beams that are reflected off of your pupil. We measure specifically fixations, and we extrapolate between those fixations saccades. So a fixation is a pause at a particular location that you're looking at for a threshold of, in this case, 1/10 of a second. And saccades are the pathways between those fixations. Through the recording and calculating of those 2 measures, we can describe your visual search task. So how do we apply this equipment in this particular design? Let's talk about experiment number 1. So the first question we had is, what are some of the causal factors that result in a right hook crash with particular concern for the motorist? What are their contributing factors? And we wanted to very specifically understand how measures of visual attention, situational awareness, and crash avoidance relate to crash outcomes when cars are turning right in proximity to bicycles. When we design experiments, any experiment dealing with human subjects, we want to think about our factorial design. The individual independent variables that we considered in this experiment included the relative position of the bicyclist. So where was the bike in relation to the position of the car? Just as Chris had mentioned, the speed of that approaching bicyclist, the presence of oncoming vehicular traffic, and the presence of conflicting pedestrians. And really we're asking the overarching question, how does the presence of adjacent traffic influence this occurrence? In order to extract more consistent measurements that we can analyze statistically, we build test tracks and we randomize the presentation of scenarios. This is an example of a single test track where you can see a series of right turns, 1, 2, and 3 in this particular grid that are designed into a course that varies with each individual presentation. So we randomize the scenarios in order to increase the statistical power of the measurements that we make in the lab. So exactly what did we do in experiment number 1? We generated 67 participants, 16 of which experienced simulator sickness. So one of the powers of laboratory experimentation is the ability to control all of the extraneous variables. That's an advantage. A downside of driving simulation is that we have a tendency to make folks nauseous when participating. So simulator sickness is a particularly interesting phenomenon. We can touch on it later on. In our lab, in the experiments that we've interacted with, we see sim sickness rates in the areas of 10 to 30%, depending on what we're asking our drivers to do. Unfortunately, in this case, where Chris and I are interested in right turns, that's one of the worst scenarios that we can expose drivers to. So we had slightly higher rates of sim sickness for this particular investigation. Subtracting those 16, we end up with 51 usable subjects that we can acquire data from, and we observed a little under 1,100 individual right turns. Data we acquired included their visual attention, as measured by our eye tracking system, Saget responses. That's a particular technique for measuring situational awareness. We'll talk a little bit about that in a bit. The observation of crashes. Did a subject vehicle actually collide with a bicycle in the virtual world? And then the position and location of all the different dynamic elements. Our subject vehicle, adjacent cars, adjacent bikes, adjacent pedestrians. So how do we think about reducing down some of those performance measures? Let's start with visual attention. When you're thinking about the driving task, the control of an automobile, your visual attention is highly correlated with your cognition. That's why it's a measure that we're particularly interested. And when you're thinking about trying to explain why crashes occur, asking the question, did you in fact see the hazard, is one of the first steps. When we reduce our data, we define areas of interest. These little rectangles describe particular areas of interest that we considered in this particular experiment. So we build tracking windows around the bikes, the cars, the pedestrians, the traffic signals, anything in the built environment that we are interested in asking the question around, did you look at that particular location during this window of time while you were performing a certain task? One way to think about that, that particular set of data is through average fixation durations. How much time during that task did you look at that object? This is some of that visual attention data for a particularly complex scenario. So this is a scenario that included the presence of a pedestrian in the conflicting crosswalk. It included a high-speed bicyclist. It included conflicting vehicles making left turns in front of our subject car. And what you find is higher rates of visual attention applied to some of those foveal hazards, like the pedestrian in the conflicting crosswalk or the oncoming vehicle. Comparatively, we see very low rates of observation for that adjacent bicyclist. One interesting takeaway, those are average values bounded by 95% confidence intervals. Situational awareness as a construct is pretty useful when we're trying to describe causal factors. There's a bunch of different ways to think about it. The model that we used as defined by Saget includes 3 levels of situational awareness. Level 1 defines your visual attention and the likelihood that you identified a hazard. Did you see that risk in your near proximity? Level 3 asks the question, once you've identified that risk, how do you consider the conflict between those trajectories into the future? Do you understand if you're going to collide with that object or if an avoidance maneuver needs to take place? In order to measure these, we froze our simulation experiment either immediately during or immediately after the right turns took place, depending on what we were trying to measure, and we asked a series of designed questions that we then benchmark against the real data from the study. So questions at the level 1 might be, did you see the presence of the bicycle immediately adjacent to you? Questions at level 3 might deal with projecting times into the future. How long would it take before you would collide with that fixed object? Was that pedestrian going to be hit by that motorist? Things of that sort. The thing that's particularly interesting when we look at the overall situational awareness, that's the measure that most folks use in the research to define how this influences your crash likelihood. In the base condition where we strip away all the variables, we have the highest level of correctness. And as we introduce opposing vehicles and then bicyclists ahead or bicyclists behind, your performance in situational awareness decreases. You are less aware of their presence, and you are less likely to correctly predict how to avoid a crash.
All right. So one advantage that, or one innovation that Dave and his team were able to make in the simulator experiment on this research is that they were able to define this and extract the centroid and the time and position of all actors in the simulator. So from that measure, we were able to, for every time that a bike and a car interacted, we were able to extract this measure called time to collision. And in the simulator, the time to collision, well, this is a picture showing the calculations for the time to collision. In reality, a time to collision value is not a constant measurement. So when 2 vehicles are going to collide, of course, they start to take some evasive action. Unless they're not paying attention at all, then the time to collision would stay the same. But usually there's braking or maneuvers, and so that time to collision changes over time. In our simulator experiment, the bicycle speed was fixed. So the bicycle speed never changed. So even if the car was in front of it, it just kept going. It's a limitation of what we had to work with in the experiment. So the speed of the time to collision value we could measure when the car turned over the bike's path, that time to collision value would be a fixed number. Which in the field, it's very difficult to measure the time to collisions because people will change their speed. Cars will change their speed. So we have to measure a different time called post-encroachment time. And this is basically the time difference between when two objects intersect the same point in space. So I'll show you a picture a bit later on. But for the most part, because of our constraint in the simulator, these two values were relatively comparable. And so we did, and I'll show you in the next slide that we in our field validation. But looking in a little bit deeper into those 1,000 right turns, there were actually 26 collisions that we observed in the first simulator experiment. And of those 26 collisions, 60% of the drivers didn't check their mirror before turning. 5% of them looked, and we could see that they identified the bicycle object of interest, but in the reported follow-up questions, apparently didn't see the cyclist. And then, as Dave was mentioning, those situational awareness questions, 18% of them admitted or assumed that the bicycle would yield, and there was enough time to sort of turn in front of the cyclist. We were then also able to sort of look at these time to collision values and the distribution of them, and we can measure them. We binned them and looked at. There's quite a bit of research on these time to collision values, on what the thresholds are, and what are these are 3-second time to collision values. So on this end, on the far end, 2.5 to 3 seconds. But these are the severe and moderately severe ones that we considered, and the literature considers. Time to collision values that are severe enough to look at. So we dug into these near collisions in a little bit more detail. There were 408 right turns, and we had 28 near collisions observed. So in those risk factors were pretty similar to the collision or the data from the actual collisions. So there's a lot of work, a lot of research in the crash analysis that conflicts are foreshadowing of actual crashes, and we did see that sort of in the same outcomes here, that our near collisions exhibited a lot of the same failure mechanisms that the collisions exhibited. And you can see, actually I should have pointed out in this picture, this is the cyclist in the driver's in the simulator, so running right into the cyclist in the crash. Okay, so to compare the performance in the simulator with actual driver experience in the field, we had to look quite hard actually to find an intersection that there would be sufficient right turns without a right turn lane, because we're going to do some video data collection. We want a number of events. So there's lots of places where we could find where there wasn't a right turn lane, but there probably wouldn't be a lot of right turns. So we could record a lot of video, and we wouldn't get very many things to compare. So we looked for a place that was sort of like kind of on the threshold of needing a right turn lane, because right turn lanes usually go with right turning volume. So we found one location. We looked all over Corvallis, and we looked a lot of, I don't know if is Ali in here? I think Teresa, did you help? Anyways, we looked at a lot of places trying to find the right situation. We found Interstate and Going was one of the ones that we looked at. So all of our video was collected here. It was from November to February. We had 144 hours of video. And what we did is for all of the right turning bicycle car interactions, we marked the same point in the middle of the bicycle path and then measured when the car went over the path and then when the bicycle went over the path. And we called that's the post-encroachment time. And we extracted 43 events where the post-encroachment time was less than 5 seconds. And then here's the graphical comparison of how those distributions matched with the simulator, with the extracted time to collision values from the simulator. And so one thing you see is that in the field, in the simulator, there was a lot of scenarios that we called crash likely, where we loaded up, the bicycle was going fast, it was coming from behind. Those scenarios don't occur quite as often in the field, and so some of these lower time to collision values, there isn't as many. Actually, there's none in this severe time to collision value. The blue is observed in the field, and the pink is observed in the simulator. So the simulator, you see, there are more frequent observations than we saw in the field, but the shape of the distribution of those time to collision values were, and from our statistical tests, we determined that they were comparable. So we were quite satisfied that the behavior in the field was a good matching with the behaviors in the simulator. So after that step, we moved to experiment 2.
Thanks, Chris. So in experiment 2, we're asking the question, now that we think we understand something about why these crashes are occurring, at least on behalf of the motorist and some of the adjacent traffic, what can we do about it as transportation professionals? Are there treatments we could apply to intersections to reduce the likelihood of this particular outcome? So what would those countermeasures be? How would they perform comparatively against one another? And could, at the end of this sequence of experiments, could we make recommendations to ODOT as to what they might consider at high-risk locations moving forward? We spent an awful lot of time talking to DOT designers and traffic engineers, shortlisting different alternatives that we might be able to implement. We also scanned, it was on the order of 175 journal articles, all discussing right hooks and right turn crashes. And we came up with a list of signs, pavement marking alternatives, modifications to curb returns, and then a relatively novel approach, at least at the time we were doing this work, in terms of a protected intersection. One of the neat things about this sequence of designs was we developed some new coding protocols that would let us take Civil 3D design files from ODOT specifications and render them directly into our laboratory. So our graduate students did a fantastic job adding that capability to our toolbox for this particular lab. In terms of the experimental protocols, a very similar mechanism was used, a series of test tracks where we randomized presentations of different combinations of those individual treatments to try and isolate variables and understand how they performed against one another. We recorded the same driver performance measurements from experiment 1 in experiment 2. Here's an example test track. In total for the second experiment, we had 46 individual participants. We lost 18 to simulator sickness, giving us 28 usable observations and a total of 616 crashes, collecting a similar cross-section of performance measures. An example screen capture from one of our scenarios with a cyclist leading the subject's automobile. So I'll show you a couple of alternative visualizations. Here is a heat map thinking about the visual attention of our users. Resolution's a little bit low, but you can see the traffic sign treatment that we're considering here, and that a bit of visual attention was allocated there. We had conflicting vehicular movements, and folks were looking at that. And in this case, we also had a longitudinal bicycle lane tracked across the roadway, and there's some attention paid there as well. We can look at the areas of attention as we get close to the intersection, tracking across a solid green bike lane with dashed white lines to either edge, and glance patterns on the conflicting vehicular movements. Another way to think about that visual attention is to isolate two scenarios where we introduce a particular treatment in one and remove it in another and try and understand what happens. This is the comparison between our two sign alternatives. So there is no warning sign or there is a warning sign. In most cases, we see an increase in the visual attention allocated to the bicyclist in the presence of the warning sign. However, it's not statistically significant in nature. So if you look at increases in glance patterns towards the side mirror or the bicyclist in the side mirror, but the 95% confidence intervals don't allow us to say statistically that that's a change, although the average fixation durations do increase. A second element of visual attention that we considered was the frequency of fixations. So how many times did you, in fact, look at those objects? And we saw a 3% shift up in the presence of the sign of observations on the cyclist. When we think about crash avoidance, we came up with another potential measure of value. So we were curious as to the speeds that the vehicles were traveling when a collision or a near crash took place. In this particular comparison, we're looking at the presence of the protected intersection or not, and we're comparing the time to collision values for the interactions between the drivers and the bicyclists. And what we see is a fairly dramatic shift in those time to collision measures. So when we introduce the protected designs, we see far fewer conflicts in the 1.5 second and 0.9 second threshold. So we're generating more positive separation between our vehicles and our cyclists with that alternative design. When we look at the speeds for those crashes and near misses, and this is a comparison thinking about the curb return, so how sharp are the curbs at an intersection. When we use a 10-foot curb return, so a sharper curve, we see a slight reduction in the speeds of the crashes, but a fairly substantive reduction in variability. And when we talk about frequencies of collisions, speed variability is one of those factors that a lot of folks say contribute to the number of interactions that occur. So we look at that as a positive shift as well. So in the final comparison, each treatment was evaluated in terms of its impacts on the driver's visual attention, its impacts on crash avoidance, did crashes or near misses occur, and the severity of the crashes that were observed. What were the speeds upon the point of impact or in those near collision cases? And the research team, we really mulled over these alternatives quite a bit. The dashes here represent no definable change. The check marks represent positive impacts. The X's represent negative impacts, and we were looking for clusters of observations. Remember that all of these individual performance measures, they're surrogates for the potential implications of safety and can, in some instances, be difficult to differentiate. Our recommendations, based on the observations from the experiment, were that we saw generally positive outcomes from the implementation of the sign. A bit of a surprise to us, but these two alternative pavement markings performed the best. That was unexpected. We would have thought the green stripes would have dramatically improved performance, at least within the context of this experiment. We didn't see that to be the case. The dashed white lines with stencils generated the most positive, consistent outcomes. The protected intersection had dramatically positive outcomes, and the reduction in curb radii had positive outcomes based on those particular surrogate safety measures in this particular experimental scenario. With that, I want to make a couple of acknowledgments. So first, both Chris and I want to recognize the contribution of ODOT, who funded the research. Without them, we couldn't have had the chance to work together over the last year and a half as a part of this particular study. And none of this would have been possible without a fairly comprehensive list of graduate and undergraduate students working in concert with one another, both at Portland State University and Oregon State University. So on this very project, we had one student at OSU finish a PhD dissertation, two students, one here at PSU and one at OSU, do their master's degrees. And then we had 4 undergraduate research assistants who helped us reduce data and design some of the experimental environments. And with that, we'll go ahead and open it up to questions. Sure.
Thanks so much for doing the research and also paring down your really big report to a very concise 20-minute presentation.
For those who didn't read it, I think we were over 200 pages,
yeah.
So there's a lot more. Yeah.
I was wondering if you were able to control for, I guess what I call education or familiarity with cycling. So were there drivers from environments where bicycling is common, and you notice the difference between them and drivers from environments where bicycling is less common? And then the other question was, were you able to test under low light conditions?
All great questions. When we think about some of the demographic information that we collected, you're constrained in that laboratory setting by access to folks that live near where the lab is. Most of the folks come from the greater Corvallis area, and in general, I would say that that makes most motorists relatively familiar with bicyclist travel. Are there potential implications if we engage participants who lived in environments where there's a really small mode share for cycling? absolutely a potential contributor, not something that we were able to tease out from this particular data set. When you talk about low light conditions, we can model nighttime running. There's a reasonably sophisticated model for how headlights work and how things like the conspicuity of individual objects, how they change. I tend to shy away from nighttime studies in simulators personally for a whole bunch of fidelity reasons. So we didn't study that, although the visibility of cyclists is a really important question. So not one that we delved into here.
I think one thing we should mention is that the subjects in the experiment didn't know what we were studying. So I guess that's another question we often get. So they were bicyclists. They passed bicyclists. Sometimes they didn't. They know they were making a lot of right turns, but they didn't know what particular piece we were studying about their driving. Yeah.
Michael Flynn, Civil Engineering. On a slide near the end, survey was the fourth or last row. I was just wondering what was meant by that.
So we conducted both pre and post surveys in the driving simulator lab for every individual subject. We also conducted some larger scale surveys as a part of some of the graduate thesis work. The surveys were focused around comprehension of different treatment alternatives. So those were higher or lower rates of comprehension on survey questions administered, some before and some after the experimental drives. Yeah.
So I'm interested in your findings about the green crossings not actually being preferable to the dash crossings. And that actually fits with some of the research that's come out of Copenhagen with the blue crossings. But I think intuitively, we think that it should work, and so we keep doing it. And so I wonder your thoughts on that, and then secondarily, if you could speak to how you think that actually might affect whether or not we should paint protected intersections.
It's a great question. In that lit review that we conducted, we also came across those findings that the blue pavement markings generated better results for protecting cyclists. And in fact, if I understand this correctly, a number of years ago, Portland tried blue markings first before the U.S. turned towards the green as the default in the MUTCD. So that was something of interest to us. The observations here lead me to think that we may be able to save on maintenance investments, and we may be able to apply lane markings across more intersections because they're a little bit cheaper with the dash configurations and just the stencils. But I think we want to be cautious about any one experiment changing design practices. So I'd really like to see others reproduce some of these observations in a few different ways before we knew with more certainty whether that's the right sort of cost-benefit to apply.
Yeah.
The thing that was interesting to me about the Copenhagen study, so just to be clear, I'm talking about the one where Jensen went to the blue markings. Actually, he found that one blue marking was effective at crush reduction, but 4 was not, and so the 4 were not. So that's what I think is sort of counterintuitive for us. So we tend to think, that more paint is actually better. So this fits, I think, with what he found.
Yeah, I think we talked a lot about these results because there was a lot of them, and we were trying to distill it down to this check mark. And so we were looking at statistical significance and change, and so I think we probably spent 3 weeks, I think, trying to interpret all of these. And I think one thing we did hypothesize about the green marking is that it drew some attention away, because our primary measure was the cyclist attention to the cyclist, and maybe the novelty of it maybe drew a little bit more attention to the pavement marking itself rather than the cyclist. But it was, I think our indication was that some type of pavement marking was good, and we were looking at the difference between the white and the green. We just didn't see enough in this particular experiment to recommend the cost of the green markings.
Can I ask a related question? Because on your 2 protected intersections, the difference between those is green, and the green was better than no, which is sort of the opposite of your pavement markings here, where green was worse than no green. Any speculation on why the difference?
That's a great question. It's twofold. We probably could have spent a little bit more time describing how we coded a protected intersection. There's also islands, physical islands with curbing that separate the corners of that. Yeah, you want to point them out? It's not just
these
the green.
little corner islands.
Okay, we're more physical on were an actual concrete island.
Yeah, so that's a 6-inch raised curb in those particular specs, and it also shifts the stop line around because we have another bike lane that comes in front. Really, the idea in our minds is we're shifting the relative position of the vehicle and the bicyclist in that protected construct. So rather than having the bicyclist be immediately behind you and then connecting in the intersection, we're shifting them slightly to the right and in front of you, potentially for a collision to occur. And from a situational awareness standpoint, they're more visible because their relative position to the driver changes.
So that difference is more due not to the green paint, but to the perhaps
right. And that, nobody in our experiment had seen one of those before. So in the survey question, they often, their interpretation of where they should go was incorrect. But once you put the green in it, they're like, oh, I'm not supposed to go in there. So, and the limitations of what we can, this is the design that we showed. So.
On PM4, can you talk a little bit about the difference between the negative effect on visual attention, but the positive effect on both crash avoidance and crash severity?
And some of this comes down to trying to distill the statistics into a really consumable chunk. So relatively small positive movements on crash avoidance and potential crash severity, but a pretty big movement on visual attention. That's where we sort of draw that conclusion from, but it was a lot of debating.
That was the hypothesis, especially that last one with all that green paint. We saw it took a little bit away from the attention to the bicyclist, either in the mirror or the side mirror.
Miguel.
Just to clarify, so when the driver is turning right, is there any other traffic ahead or behind or to the side that could be distracting the driver?
So in the worst case scenario that we identified in that first experiment was as our driver approaches the intersection, 2 vehicles make a left turn in front of their path, and a pedestrian is in the conflicting crosswalk. So that was the traffic loading. We always go back and forth between how much ambient traffic we include and how prescriptive the individual players are. And what we have leaned on in the past is we have to keep ourselves to about 24 different scenarios, so we're limited in the number of iterations we can test in any one shot. So that was the loading in this particular case.
So my follow-up question is, now that you learned all this, and if you were to continue with this project, what would you do next, or what would you do different? There are so many options we can study.
Yeah, absolutely. To me, I think it would be trying to expand upon the alternative treatments that we're focusing on, and I would probably try and pay a little more attention to crash likely scenarios within the context of the treatment experiment. I would lean a little bit more there. I think we learned a lot from the crash likely scenarios from experiment number 1. Some work that we're starting next is also this entirely focused on the motorist's contribution and the surrounding traffic. There's also a question in our minds as to what's happening in the bicyclist decision-making to stop and go and where they situate themselves in relation to potential blind zones of the motorist. And we think there's some really neat work to do there. So those would be 2 off the top of my head. Yeah?
Would you allow drivers to play with their gadgets and phones as they would?
That's an outstanding question. I think distraction and just transportation human factors more broadly overlays all of these sort of design questions and crash outcomes. In this particular experiment, we didn't do any distraction study, but that's certainly going to confound some of those performance results. So if we think that things like visual attention or situational awareness or time to collision are factors that give us insight into these outcomes, if we overlay distraction on top of that, all those performance measures degrade. And that's what I would expect in that particular scenario. But obviously a great question.
Yeah, and then the other thing I just remembered too, in the field validation at that intersection, we didn't have any conflicting left turns because it was a protected left turn. So there were no, in the field validation, the drivers didn't interact with left turns. And there were only a handful of places where they interacted with a pedestrian and a bike. So we didn't really get to sort of look at the performance of the driver against those two other variables. So we just isolated the simulator where it was just bike and car interacting, and then in the field it was bike-car.
I have a question that relates to, I guess, the relative novelty of some of the treatments, and your comments about how your hypothesis is that because these are novel treatments that they may be capturing visual attention to a greater degree. Is there any observations or science around how that might change with familiarity? So if we were to, again, maybe you're selecting from a pool of users or drivers who this wouldn't be familiar to, or would be familiar to, would their visual attention be different? Or if you tested these folks again after some period of time when they've been more exposed to this, would their visual attention be different?
You can certainly see shifts within the context of driving simulator studies longitudinally. When you expose folks to novel traffic control devices, let's talk about that most broadly. Probably one relevant example to the Oregon context that comes to my mind would be flashing yellow arrows for permissive left turns. If you can think back to the first time you interacted with that particular indication, or if you watch folks who haven't seen them before interact with them, they'll have quite different responses than they would after a few engagements. So there's absolutely calibration that happens over time, and that varies. I don't know of too many studies that have thought about that within the context of intersection approaches specifically. But that's our thinking at the moment.
But in these conclusions and in your matrix, you're not really able to account for that.
No, yeah, that would be sort of outside the scope of this inquiry.
I mean, we did get a pretty reflective age distribution of the. Dave has access to a older driver panel, so we did have it wasn't all college students, but they were all people from around Corvallis, and there are some green markings in Corvallis, aren't there?
Yeah, there sure are. So when we think about building a representative sample, we start with DMV records. We use 10 years of historic data from the state of Oregon. What do our licensed drivers look like? And then we build our distribution around predominantly gender and age. So our range of subjects in this study was 18 to 75 with a median age of something like 42 and a half. That's from memory, but it was close to that. We do a pretty good job of trying to replicate the driving population in Oregon from that standpoint. Yeah.
So about the recommendation, my name is Jan, civil engineering student. So about the recommendation, do you think if we install a flashlight with vehicle detect sensor, that would cause less crash?
Specifically, less right hook crashes? That's an interesting question. The closest designs that I can think of would be advanced warning signs with flashing beacons for like isolated high-speed signalized intersections. And most of the work that I've reviewed that has examined that demonstrates reasonably positive contributions. So perhaps, I think there are a host of alternatives that we could consider to reduce crash frequencies of this type.
Yeah, I mean, certainly it has implications for, connected vehicles or, future technologies that, that sensing, knowing that this is a clear weakness of the driver to detect this hazard from behind at high speeds. So.
Justin Hurwitz, civil engineering. You had a couple of graphs that showed the differences in the signs or differences in treatment from I guess no treatment and then after. But it only showed the 0.9 and the 0.5 or 1.5 for like time to collision. Was it pretty much a kind of a similar trend, like those lines parallel as it goes up into the higher range? Like I'm just curious why it didn't show the higher.
We picked those because the literature suggests that the time to collision differentials that are the most concerning are within that 0 to 0.9 and 1 to 1.5. Those are the high risk scenarios, so we focused on those. Once you start to get beyond that, those are not. It's not necessarily near misses. Yeah.
I've never heard of this simulator sickness phenomenon before, and I'm wondering if there's evidence out there for simulator use that ensures that there isn't a lesser effect that might retard somebody's cognitive function. You know, I'm not sick, but I didn't recognize the cyclist, or I performed a lower level.
Yeah, that's a great question. So simulator sickness has been around ever since driving simulation was introduced. If we look into the literature, the first paper that ever talks about driving simulation was published in 1934. It was basically a person sitting in a diorama with no motion behind a steering wheel. And we've sort of advanced forward from there. The first instance of simulator sickness shows up from it's the training of military personnel. So one of the thrusts to build this into a platform that was usable was to train military personnel on vehicle-to-vehicle combat. That's something that's very expensive to do in the world, and it's something that can have a pretty positive effect, except the negative outcome was that a third of everyone that went through the simulator couldn't actually use that platform. And we really haven't been able to move the needle on that. There's a bunch of things we can do. We know there are things that will increase rates of simulator sickness. Things like cool, moving air, having water on site before and after. In our lab, we use the protocols from the National Advanced Driving Simulator. So they actually took some time and hired actors to demonstrate what clusters of symptoms will look like. So we track every subject very carefully, and as soon as we see even the hint of simulator sickness, we pull them out of the experiment and we don't use any of their data. Is it possible that someone is experiencing mild symptoms that could affect their performance and we don't catch it? Sure. Certainly a possibility, but it's always something that we're trying to move the needle on. And there are actually entire research labs who only focus on that one question.
I'm curious about the impact of speed. So it sounded like most of this data is based on 16 miles per hour. Is that right?
Yeah, that was in the second experiment. In the first experiment, we had 2 levels of bicycle speed, 12 and 16 miles per hour.
So I'm curious regarding steep downhill stretches. I think Professor Monsere, you might have been involved with this study a few years ago with the bike boxes going in, green bike boxes. And my takeaway from the study was that certain intersections became more dangerous for bicyclists if they're on a downhill stretch. And in some cases, the average speeds, I believe, were above 16. It might have been like 18 miles an hour. But on uphill stretches or flat stretches, they perform much better. And so, I don't know what a good design could maybe be for downhill.
Well, I think it's just, the results from the simulator and from some of those field studies, I think, and Rob was involved and Roger was involved in those, when you have bicyclists approaching queued traffic or traffic from behind at high rates of speed for a bicyclist, it's just harder for the motorist to detect that bicyclist coming from behind. So those will be places where there are elevated, our simulator experiment suggests that those would be places where we would have elevated crash experience, and the field experience also suggests that. So I just
think designers should take a very close look at topography at intersections before they make a recommendation. Because if it's uphill and the average speed is 12 miles an hour, it's a totally different ballgame than if you have several cyclists going 20 plus.
Yeah. Well, the uphill would help the speed to be slower. Hopefully. Yeah.
Uphill would help.
Yeah, Chris, in your recommendations, you mentioned, the slide where you show the treatments that you recommend. You put it in the context of it may not be, I think you talk about maintenance and not worth the expense. Can you talk about why you put it in that context a little bit rather than just talking about pure safety?
Yeah, I think that we were trying to really look at the difference between the without green and the green only, and kind of in our discussions they were pretty close, and we thought, well, the extra cost for the green might be a thing that would let you go to leave the white, just do the skip only. I don't think either one of us would say our study's conclusive on this, and that that you should stop doing those markings altogether. It's just we thought we would really see a difference, especially in that primary measure, the visual attention one of the cyclists. We thought that the connection would be somebody would see green and then look for cyclist. We didn't see that in the simulator. So I think at this point we just were a little cautious on our recommendation there. But we were also very, I think, careful not to say don't use green paint, because we were, not quite sure that we were the definitive study yet.
This isn't your recommendation.
No, that was this one. And these aren't. I mean, you could do all. I mean, you could do 3 of these at any one intersection. So they're not. You don't have to do just one. So. Yeah.
Can you go back? I think it was the bar graphs with the sign results. So back maybe 2 more there. You pointed to the ones where the having the sign was a little better, but there's a couple here, the turning vehicle, where having the sign is worse. And I didn't have enough time to think about it. So turning vehicle and Dutch intersection island, it seems like you have the opposite effect of what you would want. Is there a reason?
So you have to think about it in terms of the context of that particular location. Shifts in looking at a vehicle on your approach to the intersection that's a couple hundred feet in front of you, that's going to clear before you get there. That's not as concerning to me as actively searching for the bicyclist. So that's what we were interested in here is, did we move the needle on you actively searching for the bicyclist? If we think back to experiment number 1, in 2/3 of cases, the reason why we saw a crash or a near miss was because the subject driver did not at all search for the cyclist. They didn't look in their mirrors, they didn't look over their shoulder, they didn't look at the bicyclist when they were there. So that was the thing that we were trying to move the needle on.
This is what the person is looking at.
Yeah, those are average fixation durations. Yeah, that's the physical, yeah. So that's going to come down to control and guidance. Oh, no worries.
I was thinking a Dutch intersection with a sign or without a sign. Okay.
Yeah, we tried to just give you little snippets of the analysis that we did and then summarize it in our checkmark table, because there's a so. Yeah.
So I could be misreading it if you go forward. When you're looking at, you were interested in the visual when you had the sort of the recommendations or the slide right next to the recommendations. You had been interested in this one. You'd been interested in the visual attention because you thought that would correspond. The more they're searching for bicyclists, the more that would lead to avoiding the crashes. So inasmuch as it looks like it's not really closely related here, if you look at the PM4 there, is it important that people are clearly not scanning for cyclists when that particular design performed really well in avoidance and severity? Because to me, if someone's looking for a cyclist and they still run into them, that's less important than if they didn't see him at all, but they were able to avoid the crash. Am I making sense of that?
I would say if you don't see the hazard that you're going to interact with, you're almost certainly going to collide with it. Cognition follows visual attention in these things. If you don't see the pedestrian and you don't change your course and you're on conflicting trajectories, you're going to collide with that individual.
Which I get, but when I look at the performance there and I see that
so
particular
there's
one.
no magnitudes associated with these.
Okay.
So just could be slightly positive, could be dramatically positive. It's a summary.
The simple check mark, we debated a little bit about how to present it, and that was part of our 3 weeks, is how much do you need to get a red X? So, there was, it's an imperfect interpretation in terms of the data because not everything's statistically significant. We looked at changes, overall changes. We're looking at it relative to the other things, and so again, I just want to go back to that. These were our recommendations from this data about what seemed to be the most from these metrics that sort of had the most. But it's not to say that if we redesigned it and looked at it a different way in some more detail that we would get the same results. Yeah.
Protected intersection.
We had a good discussion about that, and they actually were pretty good. Their designers actually laid the templates out and said we could make this work at a state highway, and the TAC said, the Research Technical Advisory Committee said, let's not worry about trying to figure out all the things that you'd need to figure out. Let's just look at the geometry, and we could make it fit. So let's test it. And so I think they deserve credit for looking at it. I mean, we're calling them Dutch islands, and that's why some of the slides still had a D on them when we were working on this. So they hadn't seen any of the ones in in Davis or Salt Lake City or anything. This was all just from the conceptual drawings. So.
Are any of these treatments actually available in the vicinity of the drivers that were in the study? So could they have had some sort of pre-influence to them?
Not P1 and P2.
Technically, the curb return is within the DOT spec for ranges at intersections, so that's possible. This sign is taken directly out of a DOT manual, so that's a spec that's available to folks to use. They were interested in the fact that it showed some positive results because that's a fairly cheap installation and may be useful, so they were excited about that.
So yeah, probably some number of drivers have seen some of the treatments.
It'd be really interesting to pack up your equipment, take it to Copenhagen, run it again, and see where the Copenhageners' visual attention.
Yeah, that would be. We have a standing research hypothesis to bring some of our lab here to PSU and test cyclist behavior in Portland and compare it to what folks in Corvallis do. We're pretty interested in that question, so looking for opportunities.